Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about IPv4 addressing. Specifically, you're going to learn about IPv4 addresses, subnets, and then we'll finish it off with TCP, UDP, and IP headers. So let's go ahead and begin with a basic introduction to IPv4 addresses. An IP address is a unique logical number to a network device or interface. It is 32 bits in length, and to make the number easier to read, the dotted decimal format is used. The bits are combined into four 8-bit groups, each converted into decimal numbers. For example, as you will see here, this address is 10.128.0.1. The first octet dictates which class the IP address is in. As you see in this diagram, the beginning bits of the first octet will dictate what class the IP address is. There are 5 classes, A, B, C, D, and E, and let's go ahead and talk about each of those at this time. Class A addresses range from 0 to 127 in the first byte. Network numbers available for assignment to organizations are from 1.0.0.0 to 126.0.0.0. By default, for Class A addresses, the first byte is the network number, and then the 3 remaining bytes are the host number. Class B addresses range from 128 to 191 in the first byte. Network numbers assigned to companies or other organizations are from 128.0.0.0 to 191.255.0.0. By default, for Class B addresses, the first 2 bytes are the network number, and the remaining 2 bytes are the host number. Class C addresses range from 192 to 223 in the first byte. Network numbers assigned to companies are from 192.0.0.0 to 223.255.255.0. The format is the first 3 bytes are the network number and the last byte is the host number. Class D addresses range from 224 to 239 in the first byte. Network numbers assigned to multicast groups range from 224.0.0.1 to 239.255.255.255. Please note that these addresses do not have a host or network portion. Class E addresses range from 240 to 254 in the first byte. These addresses are reserved for experimental networks. Network 255 is reserved for the broadcast address, such as all 255s. Again, take a look at this table and you will see the summary of the IPv4 address classes. Each address class can be uniquely identified in binary by the high order bits. Now, subnetting plays an important role in IPv4 addressing, since you want to be able to break down the networks into smaller ones. As you can see here, we have a Class A IP address, and if we were to use its default subnet mask, it would be a /8. That is, the first 8 binary bits would be 1s and the rest would be 0s. But this would mean we have hundreds of thousands of IP addresses in this one subnet. Let's say we want to use this IP address on our internal network and simply assign it to one small portion of our network where there are 100 users. In that case, we would want to assign a smaller subnet, let's say a /24. So subnetting allows us to put it on a smaller network with fewer hosts. So the subnet mask is a 32-bit number in which the bits are set to 1 to identify this network portion of the address, and the 0 then identifies the host portion of the address. As you can see here, We will now set to 1 the first 24 bits, and that will mark off the subnet, which is now a /24, which means that 10.128.0/24 is a dedicated network that can host 254 hosts. Next, let's briefly cover the headers for TCP, IP, and UDP.
What you see before you is the IP header. You will need to know the functions for each of the fields you see before you. Let me cover some of the functions that you will most likely need to know for your exam and in real-world troubleshooting. First, there's the version field. The version field indicates that it is IPv4 in this instance with a value of 0100. Then there's the type of service field. This field is commonly referred to as the type of service byte. It has 8 bits used to set quality of service markings, and specifically within this field is DSCP. The 6 leftmost bits are used for DSCP, which obviously commonly is associated with quality of service marking. Next is the IP flags field. This is a 3-bit field. The second bit of this field is the DF, or do not fragment bit, and that indicates that a packet should not be fragmented. Then there's the time to live field. This is an 8-bit field that is decremented by 1 each time a packet is routed from one IP network to another. If TTL ever reaches 0, the packet is discarded. The protocol field, which is an 8-bit field, specifies what kind of data, type of data is encapsulated in the packet. TCP and UDP are common protocols identified by this field. Finally, the source address field, which is a 32-bit field indicating the source of the IPv4 packet, and then the destination address field, which again is a 32-bit destination address, which indicates the destination for that packet. Next, let's move on to the TCP segment header. Here are some of the fields you will certainly need to know. You have the source port field, which is the 16-bit field indicating the sending port number, and the destination port field, again a 16-bit field. So, for example, if you connect to howtonetwork.com, you're connecting to a destination port of 80, which is the TCP port for HTTP. The sequence number field is a 32-bit field indicating the amount of data sent during a TCP session. The sending party uses this field to make sure the receiving party actually received the data. The receiving party uses the sequence number from this field as the basis for the acknowledgement number in the next segment that it sends back to the sender. And then the window field, which is a 16-bit field, it specifies the number of bytes a sender is willing to transmit before receiving an acknowledgement from the receiver, known as the round trip time. The other IP layer 4 transport protocol is UDP. UDP is considered to be an unreliable protocol because it lacks all of the features of TCP. There's no sequence numbering, no window size, no acknowledgements. You can see here the header is quite simple. It contains only source and destination port numbers, and then a UDP checksum, and then segment length. So why use UDP? Well, it's best for servicing applications that need to maximize bandwidth and do not require acknowledgements, such as video streams or audio. And in fact, the primary protocol used to carry voice and video traffic over networks is RTP, Real-Time Transport Protocol. And that's a layer 4 protocol that is encapsulated inside of UDP.
So here's what you learned. You learned about the basics of IPv4 addressing and subnets, and then you received a brief overview of TCP, UDP, and IP headers. All this information will come in handy on your CCDA exam. Good luck in your studies.